I'll begin. Dear Father, we thank you for this day. Thank you for the students. Pray you to help us use this time wisely just to prepare for the test tomorrow, Lord. And I pray. Amen. So I did grade your quiz, guys. And so I wanted to give those back to you. And hopefully I brought them with me. Otherwise, it would be very dumb on my part. Brian? Grant? All right. John? James? Jeffrey? Brandon? And then all the way back. Abigail? Nathaniel? Alexandra? And that back. Hiram? Behind you. Jesse? Hand that back to Prince. Joshua. So no Brian and no James? All right. For the record, if you're watching, I'm going to leave them over here under the podium, or whatever this thing is, if you want to get them later. So, what? Whoa, man! Oh. My battery is dead.
I've got like 30% left on mine.
But do you have an HDMI plug?
Yes.
Really?
Yeah. At least I think this is HDMI.
I'll take you up on that.
I'm a computer science major. I doubt computer science. I wouldn't drop it. I have cheating cards next to How many possible
Where?
were they, Dr. Cook? 26?
Oh, yeah. There were 26 possible points, but only 20 that were required in the, and listen, guys, I did not get partial credit for the most part on this one. So I will. There will be a few additional bonus points on the test this time. So what you didn't earn on this quiz, perhaps you can earn on the test. Yeah. Come on, you can do it. You can do it? Ah, you can do it. It's here. Where? So I didn't, as you can see, problem 1 is not really in your course. As I told you guys, I've experimented some with, doing more Calculus 3 in this course, and that's what you're looking at here in my solution from yesteryear. It has some Calculus 3 in it. Now this number 1, I'll write up here, since I have not included in the quiz. I think we should go over it here. So we're supposed to find the parametric equations for a line that goes from 3, 5 to minus 2, 13. And so here, we want t to be 0 here, we want t to be 1 here. And so for this problem, I use a standard technique to do this. And so here's the formula. I like to think about it as a vector problem to start with. And so this is going to start at 3, 5, and then it goes plus t times the direction vector, which is formed by taking the end point and subtracting the initial point. All right, so that is 3, 5 plus t times minus 5, comma 8. And so just to collect things together here, that's 3 minus 5t and 5 plus 8t. So this is my x, this is my y. The answer, x equals to 3 minus 5t, y equals to 5 plus 8t for 0 less than or equal to t less than or equal to 1. And you should check your answer. Now, about half of you got this, and about half of you did other things. There were a couple of you who were just half right. So I said parametric equations. These are the parametric equations, right? This up here is interesting, equivalent, but not the parametric equations. This is actually a parameterization. Of the line. I mean, it's not, anyway, it's not the parametric equation. The parametric equations are equations. Okay, they have x equals to something, y equals to something. So just as a point of terminology mostly. Any questions about this? So for those of you who got it wrong, you won't get it wrong tomorrow, right? This is not a hard one. And this continues to be important throughout Calculus 3. So it's worth trying to settle for yourself, okay? Now, next problem, problem 2. I'll try to move through this fast because I know I've wasted all our time with my inane conversations about nothing with other professors. Sorry about that. I mean, one was kind of interesting. One of the professors is thinking about sending an unsolicited letter of non-recommendation about a student. Like the student, yeah, this student has done something so, in his viewpoint, unethical that it bears sending a letter. She's like, this is a fascinating story. You see why I had to stay and listen to this. I mean, but so I'm late. Sorry. Anyway, so the way I did this was to notice that t is equal to 1 over x, but then y is t squared plus 1, which means that y is 1 over x squared plus 1. And so, yeah, y is equal to 1 over x squared plus 1. That's the Cartesian equation for the path. In fact, it's a graph. Woohoo. Now, the tangent line, there's a lot of people, most of you got this wrong. And that is unfortunate because this is a pretty basic problem right here. Part B, everybody should be getting right. Not getting this right is, you should work on that. Like, you can get this one. It's not that big a deal. What you got to do to find the equation of the tangent line is you find the x velocity, the y velocity, plug in the appropriate time, in this case, time 1. So remember, dy dx is dy dt over dx dt, but then I got to plug in the time. The time here is 1, so I got a slope of minus 2. All right, great. At time 1, where am I? If I put in time 1, I get x equals to 1 and y equals to 2. So at time 1, I'm at the point 1, 2. So then point slope gives me y equals 2 minus 2 times x minus 1. Or y equals minus 2x. Now, if you wrote down y equals minus 2x and I took off points and it looks like I didn't see what you did, tell me about it, okay? I was grading in a hurry. If you feel like you got a problem right and I've taken off all the credit, please tell me about it after class, okay? It is possible I was hurrying because I had, like, it's not important why. The important thing is I am human and I will make mistakes. Some of them are on purpose. Some of them are recreational. Let's see here. Where was this? Oh, yes. L of t. Oh, yeah. So this is the parameterization of the tangent line. So the direction vector is x prime of 1, y prime of 1, which is minus 1, 2. I put this t minus 1 here. That makes L of 1 to be 1, 2, right? And so this, I would just encourage you to look at this, see what I did there. This gives you how to create the colliding tangent line. This means that the parameterization of the tangent line, it hits the point of tangency at the same time the curve hits the point of tangency. That's a colliding tangent line. So if you look at the tangent line as a trajectory, you look at the curve as a separate trajectory, they collide at the point of tangency. I get that by putting this t minus 1 here as opposed to just putting like a t. See over here, this t? So this collides with the 0.35 at time 0. for example. A lot of you got, so like, this is the thing that's messed up to me. A lot of you missed like part B of the previous problem, but got this with bells and whistles. Like you just did this easily. And to me, this problem is kind of harder than that one, but whatever. Anyway, the point is cosh squared minus sinh squared is 1, so you can solve that for cosh, you can solve that for sinh, and then there you go, that's the equation. Now, trying to think of, there's a way, one of you did it a different way, which was not wrong, but I'm trying to think of a way to discourage it. It's good though, it's good. It shows independent thinking, so it's good. Now, I think my solution right here is flawed. I don't think I've read my problem statement. So this is fine. This part is fine, all right? Like, I took my equation, I completed the square, right? And a lot of you did that too, and that's great. And it reveals it's a circle radius 2 centered at minus 1, 3. Fine, everything's fine. But you notice what I completely ignored, which has x greater than or equal to 1. Yeah, so if I really paid attention to that, and I drew this, and then I said find a parameterization, I should have said no can do, because this is x equals to 1, right? What part of this curve is x greater than or equal to 1? In other words, what part of the curve is to the right? There's a single point. So like the parameterization would be like really pathological. It would be r of 0 is that point, which is what, 1, 3. This is not, depending on how you parse definitions of things, that may or may not be considered a path. I mean, so what I think I meant to do there was maybe put a minus 1 or something so that it actually would be an interesting part of the circle, you know? Like x less than or equal to minus 1 would have been interesting. That would have just been the right half of the circle. That would have made the problem way more interesting. So I tried to just give you most of the credit if you actually had this circle put in the right place and you just ignored that. If for some reason looking at that and really thinking hard on it confused you, let me know. I'll give you points back, okay? It's hard for me to cipher that from what you wrote on the page. Yes, sir?
Would a circle have a radius of 2 or 4 here?
Oh. So the problem is interesting. And my algebra is wrong. No, the picture is wrong. What's wrong? The picture. The picture is wrong. Yes, you're right. I knew something was askew. So 4 squared. So if this is actually, as I'm doing, 1, 2, minus 1, 1, 2, 3. So I'm using one grid as one unit. Then you're right. It should be like over here. And then it would be, so it'd be like this part of the circle, right? Yes. That's what you guys, okay. If that's what you're trying to do, good. So I take it back. The problem makes sense as it's stated. It just didn't make sense to me because I'm an idiot. And apparently, I was also an idiot in 2012, which is when I wrote this. So, okay, yes.
Could you just quickly explain how you parameterize that?
Yes. Parameterization here, standard thing. I would put x plus 1 equal to 2 cosine t, and I would put y minus 3 equal to 2 sine t. So x would be minus 1 plus 2 cosine t. Y would be 3 plus 2 cosine t, right? And then, oh, good grief. Sorry. So the circle, something like that, right? So the part we're trying to parameterize, what's that? Oh, good grief. Did I do that too? Wow, I really got that too stuck in my brain. You're right, 4. Thank you. But that is a very good sign. You understand. Let's see here. That gives me hope for tomorrow. Let's see here. So 4, x greater than or equal to 1 is this piece right here, right? We're trying to parameterize this part of it, right? So this in the middle is t equals to 0. That's where cosine is biggest and sine is 0. That's the point. 2, that's 2 comma 3, right? And so you need to figure out whatever this time is, time 1. This is by symmetry minus time 1. And so you're going to go time minus time 1 less than or equal to t less than or equal to t1. How do you figure out what t1 is?
Set x equals to 1. Inside, right?
Yeah, set x equals to 1 at t equals t1. So we've got 2 equals to 4 cosine t1. So cosine t1 is equal to 1/2. So t1 is pi over 3. So that was what was supposed to happen. I'm not sure what happened with my solution here, but
So the solution isn't complete then?
no, it is not. So I am happy for your questions. Problem 5. Some people got, some people didn't. Kind of a theme for this test. It's your quiz, I mean. All right, we get through it. Actually, when do you have to leave? 10 minutes. Let me just, I'll finish this problem and then I'm going to jump ahead. Make sure you see the solution to the one I haven't written out. So to find horizontal tangents, we're looking for places with dy dt be 0, but dx dt is non-zero, right? And so dx dt is non-zero everywhere, so we're good there. But where's dy dt 0? Well, dy dt 0 means that cosine of t is 0, right? Because the derivative of sine is cosine. And so that happens at pi over 2. That's the only place it happens in the domain of consideration, which is 0 to pi. So y equals to sine of pi over 2, which is 1, is the horizontal tangent. Now, if you just tell me t equals to pi over 2, that's lovely, but that's incomplete, right? You should tell me y equals to 1 is the horizontal tangent. You're supposed to find the horizontal tangent. So that's an equation. Now, vertical tangents, we would need dx dt equal e to t to be 0. No can do. So there do not exist vertical tangents to this curve. Arc length integral, dx dt squared plus dy dt squared square root, integrate that from 0 to pi because that was the domain given. Arc length, surface area, you go 2 pi y ds, which is this is the ds up here, square root e to the 2t plus cosine squared t, close square root dt, and then multiply by 2 pi y, which in this case is 2 pi sine t. So you have to do that integral. You have to do that integral to calculate arc length. As I said up here, do not calculate. Some of you, nonetheless, were trying to calculate. See me? I'm very angry. No, not that. Why do you guys think the dt is optional? Like, have you ever seen a calculus instructor even once write an integral without the dx or dt there? Like, why do you guys think that it's okay? It's not okay. It's not okay. It's like your girlfriend tells you, "Don't call me Bubbles," and you keep calling her Bubbles or something. Like, it's not cool, you know? It's disrespectful, right? Right. Oh, this wasn't on your test, and that was not on your test. See, I have neglected to talk enough in here to you guys about centroids. I usually have centroids as an application here, but I have sadly not said enough about that in here, so I probably won't put it on your test.
Probably not.
Probably not.
I like that word, probably.
It's a word I'm fond of. Anyway, so let me skip ahead. Oops. All right, I'm going to go faster here. So to find the Cartesian, what was that? To find the Cartesian form, all I did was I multiplied by r to make my life easier. When you multiply by r, then you've got r sine theta plus 3r cosine theta plus 6, which is exactly y plus equals 3x plus 6. Great. Smarts. Problem 9. Problem 9, you guys have got to chase down your demons here. This is a problem you must not miss on the test. And many of you missed it because you did not do this correctly. All right? And so when you look at this, got to think carefully through here. You know, going from 0 to pi, great. We start out at radius 1, we go all the way out to radius 2 at pi over 2, and then we come back to 0, finally back over here at minus pi. Excuse me, we come to, that's at where? That's at 3 pi over 2, we come back to 0. So, you know, that's what that looks like. We chase through. Anyway, that's what it looks like. I won't belabor it. And so the integral has to go from 0 to 2 pi. Some of you thought 0 to pi because your picture tricked you. But it is in fact 0 to 2 pi. And that works out to 3 pi over 2. We'll come back to problem 10 in just a second here. I did not ask you the Ninja Bob question, but I could have. Oh, so the question that was on your quiz but wasn't on the solution that was most interesting, and that I think most of you got wrong, the one that was, let's see here. I think this is, which one do we, yeah, I should probably talk, there's two things I have left to talk about. Problem 10 on this test was problem 9 on your quiz. But I actually wanted to talk about problem 8 first, because the gentleman in the back can look at problem, you can look at this one later, right? So here we have, this is problem 8. We have x equals to 3/2 t squared minus 2t. And we've got y is equal to 1/3 t cubed. And I said find points on the curve with dy dx equal to what? Equal to 1, right? Well, that's not quite how I asked it, is it? I said find which points on C have tangent lines which are parallel to y equals x. Right, so if you think about the curve, if it looked like this, you're looking for, this is y equals x, right? So you're looking for like this point, maybe this point, maybe that point, right? That was supposed to be the same slope. I almost got it. Anyway, so how do you solve that? Well, what's dy dx? It's y prime, right, over x prime, which in this case is t squared divided by what? Divided by 3t minus 2. I set that equal to 1. But that gives me a quadratic in t. T squared equals to 3t minus 2, also known as t squared minus 3t plus 2 equals to 0, which is t minus 2 times t minus 1 equals to 0, which gives me t equals to 1 and t equals to 2 as the times at which we can reach parallel tangent lines to y equals x. One or two of you got this. I forget if it was one or two, but at least one of you got this, let's say that. Anyway, so then I just have to plug back in the time, so time 1 gives me what? Three halves minus 2 comma 1/3, and time 2 gives me, 3/2 of 2 squared minus 4 comma 8/3. And you could clean those up, but there you go. These are the 2 points. Those are the points on the curve which have tangent lines parallel to y equals x. What if instead of saying parallel to y equals x, I said find the points on the curve which have tangent lines perpendicular to y equals x? How would this problem change? How would your solution change?
-1.
Yeah, you'd solve for -1 instead of 1, right? And then the answer might be that there are none. I don't know. I don't know. I'd have to work it out, but they wouldn't be pretty anyway. Then there's problem 10, which is your problem 9, right? Well, any questions about the other thing before I go on here? So outside r equals to 1 and inside r equals to 2 cosine 2 theta. Did I get that 2 on your quiz?
Yeah. Yes.
Okay, good. Yeah. So this is 2 cosine 2 theta, right? And if you look at that, it's 0 at plus or minus pi over 4. So between pi over 4 and minus pi over 4, we've got like a lobe of this, this whatever you want to call this thing. Can you take over? Thank you. Sure, go on, Josh. Go on. He's got a guilty conscience, I see. Or were you being chivalrous? Is that how you, I can't say that word. There we go.
I thought you were talking to me.
Oh. Okay. So, anyway, we got 0 between at pi over 4 minus pi over 4, and again at 3 pi over 4 and 5 pi over 4. So that sets up these sort of asymptotes to the graph, right? And so we start at 0 at minus pi over 4. We go on out here, and we reach 2 at the largest at 0, right? And then you come back, and likewise, we go between pi over 4 and 3 pi over 4, which would be here. That's actually down here because it's a negative radius, right? So it's down here. And then we get 3 pi over 4 to 5 pi over 4, which would be here and here, and that swings this pedal out. And then finally 5 pi over 4 to 7 pi over 4. That would be, in principle, down here, but since it's negative, it's actually up here. So after the dust settles, we've got a 4-pedal rose, right? And, but then, not being content with that, I said find the area bounded outside r equals 1. And inside r equals 2 cosine theta. So r equals 1 is a circle. And so we're cutting off the inside of these pedals, right? So they're not getting all the way to pi over 4, are they? They're getting to like this angle and that angle. Well, but by the symmetry of the problem, you can see you can quadruple the one that's close to 0, right? So we'll focus our attention on that one. We've got to figure out what this theta naught is, though, because that's going to matter. It's not pi over 4. It's something less than pi over 4. And it's going to be where cosine of 2 theta is equal to 1/2. And so to have cosine of 2 theta equal to 1/2, that means 2 theta is pi over 3, which gives us theta naught is pi over 6. So I'm actually going to integrate from minus pi over 6 to pi over 6 to get the area. And I have to use the 1/2 r out squared minus r in squared because there is an inside and outside radius. And so that's why do I put an 8 here instead of a 4? Yeah, I won't exactly. I doubled. Since it's got also symmetry about that, the x-axis, I can just double that as well. So that gives me 4 times 2, which is 8 half pedals in total for this 4-pedal thing. And so there you go. It's apparently 8 times pi over 6 plus root 3 over 2. Maybe 4. There's a half here. So anyway, it ain't pretty, but there it is. Well, that's pretty much all I got to tell you guys. Do you have any questions? I mean, this test is what? It's on how to parameterize curves, right? How to graph parametric curves, how to find tangents, horizontal, vertical. I might ask you, about concave up, concave down. We had that second derivative rule that you should know about, right? I won't be a jerk. I won't ask you the third derivative. It's here. And it was a joke. Then what did we do? We found arc length. We found surface areas of the curves of revolution, right? I didn't talk enough about centroids to test it this semester, so you're lucky there. And what else can I tell you? We've calculated polar areas, so you need to be able to, also use polar coordinates, go back and forth from Cartesians to polars, be willing to use polars to parameterize things. Sometimes that's like really important, right? Remember how much trouble we got into this one? Was it this? Or it was either that, or maybe it was xy. I think it might have been xy times that equals to 1 or something.
Yes.
And we tried to parameterize that just using Cartesian thinking, and it just didn't go. The minute I thought use polar coordinates to guide the parameterization, then it was actually not that bad, right? So polar coordinates sometimes can be paired with, the problems of parameterization to make progress. Know how to parameterize lines, circles, ellipses, right? Hyperbolas, graph those things. Goodness, and I'm not going to test you on directrix and focus of those formulas are wonderful, but I don't expect you to memorize or anything those problems. You had homework on it. Hopefully you learned that these formulas are known and can be looked up as you need them, but they're not things I wouldn't, if you have memorized them, that's great, but I don't think that's really that interesting. I'm more interested that you know the standard equations for hyperbola, ellipse, circle, parabola, right? So if you can't tell me where the directrix is, it's just not too mission critical in here. So if I wanted to ask a question about that, I probably would restate theorem whatever it was from section 10.1 so you could use it, But it's unlikely. So, and then what do we do Wednesday? Course, in-class course evaluation, right? I've heard a rumor that I bring cookies and possibly donuts. And then, yes, differential equations. So not necessarily in that order. Probably differential equations first, cookies second. But anyway. So don't miss that class, please. Well, guys, see you tomorrow.